Oh, cool. They got a snack bar there. Cool. Right on. Okay. Well, we should be starting up here. If Kyle could maybe just verify for me that you're seeing it's a different YouTube video. We did the last hour on pandas and matplotlib, but this is on basic machine learning, which we'll cover Python and some math theory and some code a little later. And we're going to look at a really great research paper first. Let me actually put something useful to look at on the screen. I didn't get to this in the last hour. I just wanted to show you this real quick. I haven't even tried this. I just saw this on, I have like a machine learning search on Google News every day, and some startup is doing, now I don't know if you've seen ML domains, like it's from Mali, and you can sign up for a free domain for up to 12 months, but they have the right to take it away from you if you don't pay for it. And so I've seen people like complain that they signed up and then like some guy was trying to like spam keywords and he said he actually got a lot of traffic and they took it away and made the money themselves or something. But this company Comet is using a Mali domain, which is pretty cool. I went ahead and I kind of work under this name Mega Learning just to kind of keep it alive. And it's not patent, you can't trademark Mega Learning, it's too generic. But so I got megalearning.ml, but we'll see if they steal it. I don't know. But there is this company called comet.ml. They are, this is a joke. I just hate the word automagically. Like people stopped using it a couple years ago, but these guys are using it. And so look, it allows machine learning teams to automagically track their code, experiments, and data sets. Wow, I want that. So it's probably something worth looking at. There's a screenshot here I took of their website. It has Andrew Ng's name on it. Does everybody know Andrew Ng? Like he's a Stanford professor that does this. I think it's one of the more challenging machine learning Coursera courses. And so if you're familiar like with GitHub, this is trying to be the GitHub for machine learning projects. There's something in the health sciences, I forget the name now, that is pretty cool. It's sort of the same type of thing where it lets you set up experiments and publish your data set, and then other people can go, like run your experiments. And so this looks like it's trying to be that for machine learning. I just forgot to mention that in the last hour. Well, Kaggle's more for competitions, right? Do you mind if we talk about this let me give you the mic, yeah. Because I want you to talk about Kaggle just for a minute, because Rose here, next month he might present 15 minutes on Kaggle. Yeah, do you have to turn, I think you have to turn it on. Is the mic turned on? Oh, okay, cool. Tap on it for a sec. Okay, go ahead. Yeah, sorry, go ahead.
Talking to data scientists, until you get on Kaggle, you have a tier system where you can distinguish yourself as an expert or a contributor, or I don't know what the newbie term is. It might be newbie. So anyway, I got from newbie to contributor, which is the second level, in about 24 hours.
Cool.
And that was after getting kicked out of the system twice. The data I was doing.
What were you doing?
I was just adding my social media profile to my profile, which they told me to do in the description, and apparently that was spamming behavior.
What's on your social media profile? Like something evil? No, I'm just kidding. I don't know. That's weird.
About it being not appropriate, but it was like my assumewisely.com, probably the nerdiest website I think of.
Huh.
Anyway.
So Kaggle lets you store your projects and like.
GitHub, they call them kernels.
Okay.
It's very GitHub-like. So you can fork stuff.
Oh, interesting.
So you have to submit to a competition as part of your final project. And I basically just forked someone else's work and submitted their entry level. They have an entry level. We have to predict if someone's going to die in the Titanic.
Oh, interesting. Oh, right, the Titanic thing. Yeah, yeah.
So I forked someone else's. He had everything. I ran it. I got 78%.
Wow.
I'm in the 78 percentile. So now I'm going through that and actually learning what I did.
So you can actually get a ranking on Kaggle with just 78% accuracy?
So 78% of people did worse than I did.
Oh, gotcha. Oh, that's different. Okay, that's pretty good then, yeah.
Well, there's like 15 people who have a 100%, which I didn't know what the word overfit
right
meant, but I could look at that and go, that's not right.
Yeah, that seems wrong.
That's not good.
Yeah, but the whole point about Kaggle, if you're not familiar with Kaggle, and just before we jump into the main part of this lecture, yeah, go ahead and turn that mic off. Before we jump into the main part of the lecture, people get into data science, the putting the term data science in a meetup, catches people's attention because they know that if they become a data scientist, they'll make $126,000 a year. That's like Now, I think you maybe have to work in San Francisco to make that. I don't know if you make that working in Utah County. Maybe you do, but it's one of these professions that nobody really knows what it means. There's kind of a joke about if you're a statistician and you can program, you're a data scientist, or if you're a programmer that knows some statistics, you're a data scientist. I think people are figuring out more and more, what data science means. But if you can do well on Kaggle, that is a ticket to a good job. If you can be one of these top-ranking people on Kaggle, they run machine learning prediction competitions, like the Titanic. You get this data set, and we'll actually explore some of these issues a little bit later on about like training sets versus holdout data. But if you can get a pretty high accuracy rating or prediction rating, you're going to write yourself a ticket to a good job. You'll have people recruiting you. I don't know if that's the top 1% on Kaggle, or have you seen anything like that, Ro? Or
so they have competitions that you'll don't have in my friends.
yeah, go ahead, please. Yeah, sorry. We'll just kind of keep the mic in the middle of the room there. We're just using the mic so that hopefully the audio comes through the overhead and then gets into this mic so people at home can hear him.
Yes, they have competitions that are paid. So you can submit, and if you win, you get the money.
Oh, wow. That's pretty cool. Is that betting? Can you do that in Utah? Can you bet like that in Utah? I'm just kidding. It sounds like betting.
I don't know. It's not.
I'm just joking.
I'm not putting my money.
Yeah.
Well, it's like insurance companies want to figure out, like, I know one of the ones I was looking at, one of the insurance companies was trying to take some images.
Hold it up a little closer.
They were trying to take some images, and in the images showed whether somebody was doing some kind of inattentive driving.
Oh, really?
They were supposed to run it through some deep neural net to see
how well, yeah. I'm going to shut this door here because we're getting too much noise. That whole thing of insurance companies putting sensors on your car so they can track your driving, I see why they want to do it, but it's scary. I like to have an old car that doesn't have too many computers on it, but I'm paranoid, so.
The original question was, Kaggle has something similar.
It's okay.
It's kernel, GitHub-ish, where you can fork other people's stuff and publish. And so I'm wondering if this is.
Yeah, and I haven't looked into this too. I think my impression is this isn't at all about competitions. This is just all about being able to reproduce your work. But yeah, I don't know. It's just another startup, and I think they're in Belgium or something. So Belgium's nice if you've ever been there. I like the Flemish part of Belgium. Okay, so let me close this out. We're going to go into the plan for the hour here. So there's this paper out there. This guy's name is really great. It's Shmuley, which, if anybody remembers, there was a Shmuley radio host, but it's not the same guy. He did this paper back in 2010, and I want to explain to you just for a couple minutes why I found this interesting. I got interested. I was telling Kyle before we started. I got interested in machine learning around 2012. I was watching Mad Money one day. With Jim Cramer. If you've ever seen that show, this crazy stock market guy with a bunch of special effects, and he brings on this guy named Vivek Ranadive. If I'm probably butchering his name, but he's the CEO of a company called Tibco. And he talked about they have the 2-second advantage because they know your customer is mad at you before your customer knows they're mad at you. And he gave some examples of how in a casino, they can actually track player patterns and figure out, over time, they can figure out that when you come up on a $200 loss, you're going to walk away and go across the street to another casino. And they also know you like to watch shows. So they'll actually see, as they track your profile, and they'll predict that you're about to leave and get mad at them. And they'll send a manager up and offer you some discounted show tickets or find some way to keep you in the casino. With this unfortunate thing in Vegas, things are coming out about how they can track people. The casinos have an amazing information. If you ever want to get into data science, that's probably, and you're not against casinos, not a lot of casinos here in Provo, right? But that's probably a great place to go work on data science because there's a lot of opportunity for tracking profiles and for prediction. Well, if you think about it, so that's kind of how I got interested in this stuff. And for a few years, I as old as I am, I'm 50 now, and for what it's worth, I'm going to graduate finally, my first bachelor's degree ever. Never needed one, right? Until I got interested in machine learning, and I figured out maybe I'm just not as disciplined as I need to be, but it was useful to go through some get my advanced calculus 3, get calculus 3, get linear algebra, do some algorithms classes. But for the last few years, I've kind of been going to school on and off, and I started out at UVU, and I had a couple of teachers there, like a woman that teaches topology, and I thought, there must be something about topology. It's really advanced study of shapes, and I thought there must be some way that data can like take on a shape, and if you can see when that shape is about to change, you can make a prediction. But she said, no, machine learning is pretty much all statistics. And people have probably heard this. If you want to do machine learning, you need to know statistics. Well, I heard that for like 5 years, and then I finally got up to U of U for a while, and it's a longer story, and it involves medical problems why I came back to UVU. I'm graduating. And I actually got accepted for the machine learning program at Georgia Tech. It's like an all online. If you want to do a master's degree, a $6,600 master's degree, Georgia Tech, at least on campus, is the number 10 rated school for computer science and number 6 for artificial intelligence. I don't know if that rating applies to their online program, but it sounds good, right? But it took me like 5 years to figure out statistics and machine learning are not the same thing. I started taking some classes at U of U. There's a great professor who in the second part of this hour and 15 minutes or hour and a half, we'll take a look at this guy, Jeff Phillips, and some things he's published. And he said, statistics is not, it's not what you really need for machine learning. It sounds like it is, but a lot of statistical methods are looking backward. They're taking an existing data set and just saying, can we explain what we're seeing in this existing data? Now we're going to start stepping through some quotes from this paper. If your eyes start to glaze over, it's not going to bug me if you leave the room for 10 or 20 minutes and then come back for the more interesting math and machine learning stuff. But I think it's interesting for me to know that a lot of machine learning is actually done computationally. If anyone's ever done like numeric analysis, or if you know from a math standpoint what a computational approach means, like we're used to thinking of math as I'm going to have some data, and I'm going to have a model that describes this data, and it's a single formula that exactly explains this data. And people tend to think in the world of statistics in that model. They tend to think of very precise answers and having one answer that covers all your data. If you look at, we'll jump in here in a minute, but I just want to give a little background on this. It wasn't until I found this guy, Professor Phillips, who teaches classes on computational topology and computational geometry, which I didn't take. That stuff's over my head. But apparently, a lot of machine learning problems don't require an answer within 0.1% of the truth. A lot of these problems just require 5% accuracy, or within 5%. A lot of these things in machine learning are not like solving an equation. It's not, the goal is not to say that you know the model of your data. The goal is just to be able to analyze your data and predict accurately. So like as the overview on what we're going to dive into here, there's really like 2 ways of looking at data analysis. And if you understand this, if you're doing an experiment, you have to decide up front if you're explaining or predicting. So I call it Looking Backward. That's also a book that if you're old enough, you had to read this. It's one of these dystopian books. Who's heard of Looking Backward, the English or whatever? Okay, I'm old. Yeah, you guys probably don't read this dystopian. Do you guys read 1984 in high school anymore? Okay, it's one of those kind of. So, and when I was reading it, it wasn't 1984 yet. But so I wanted to show you this guy named Galit Shmuley, I think is how you say it. If you search the paper to explain or predict, I always find it on the Berkeley statistics website, but he's actually from University of Maryland. And so if you bear with me for about like 10 slides or something, we're going to just look at some excerpts from the paper. I will show you the paper real quick. In later sections, we're not going to get into, he talks about the Netflix prize. And you know what, let me just triple check. Am I broadcasting okay there? Looks like I should be. Cool, thank you. If you look here, in the later sections, he actually gets into the Netflix prize, which if you haven't heard of that was a machine learning contest, and I think it was like $1 million prize. And then they didn't use the algorithm, right? I guess, I don't know why, I never quite figured out why they didn't actually use it, but somebody won a bunch of money, because Netflix has this, are you familiar with this? They have this prediction recommendation. That's like a big part of machine learning, is if you're on Amazon and you look up, a green paintbrush, you're going to see, oh, it's going to start suggesting a bunch of paint for you, right? So they look at the purchase patterns. They have this huge data set, and they look at all the patterns they can find in there, whether they know what the pattern is or not, and they can recommend things. So and Netflix is excellent at this. You go watch a couple movies on Netflix, and pretty soon you're seeing movies that are going to be interesting to you, and that is totally customized for you. And Netflix doesn't care like what the underlying well, let me just ask, does anybody have like a statistics background or statistics training? Okay, so you guys kind of know roughly when I say a model, well, it'll come out as we talk here, but I mean, a lot of statistics people think I'm going to come up with a hypothesis, and then I'm going to run a hypothesis test and either accept or reject my hypothesis. Do you care what the hypothesis is if you're doing movie recommendations? No, you just care that people keep signing up and that people like the movies you recommend. There can be so much data that you don't actually need to know what the model is. You just need to know that the prediction works right. And that people from a standard statistics background hate that. It doesn't feel comfortable. And so Shmuley in this paper is kind of arguing that a lot of data analysis is locked into this statistical mindset when it needs to move to a predictive mindset. Let me go to the top of the paper. So it's called To Explain or Predict. We'll look at something out of the abstract here. He says that, and forgive me for reading, it's not normally a good form to read off of slides, but I want to just make sure that we hit some of the highlights here. So he says, and is that readable? Yeah. There's a near exclusive use of statistical modeling for causal explanation. And this is, to me, this is the key part. There's an assumption that models with high explanatory power are inherently predictive. And he's making an argument that just because your regression line fits your data with a really high R squared, if anybody knows what that means, it means that if you have data and there is a trend, you're drawing a line that every point along that line is like on average an equal distance from that line. That's the best fit. And sometimes data fits a line better than other times. But just because you can draw a line through some data doesn't necessarily mean that the next data point is going to fit on that line. He talks about here, so he's talking about causal explanation. Then he gets over to different fields like NLP, natural language processing. If you use Siri, if you talk to any of these, I hate these automated systems where you have to say customer service. If you ever speak in your natural voice and it's like, what? I didn't understand you. And I have developed this voice like this for speaking to automated systems so that they seem to understand better with better enunciation. I don't know, but it's annoying. And so NLP is not only voice recognition, but it's also text analysis. Empirical prediction just means based on the actual things that you see. It's not theoretical. Empiricism means that you're actually looking at what's happening in front of you to draw your conclusions and not basing it on a theory. So he's saying in these fields like bioinformatics, the focus is more on empirical prediction, and they don't really get much into causal explanation. In his paper, he says, my main premise is the two are often conflated, yet causal versus predictive distinction has a large impact. And to me, this is really critical, has a large impact on every step of statistical modeling. So if you're going to do some kind of an experiment or hypothesis, and you don't have this in mind, that you're starting out trying to explain something versus predict, it's going to change. If you're not aware of it, you're just going to probably take the explain approach and not come up with a good predictive model. But if you know the difference, you can actually get your early steps better in how you handle data. So let's just take a few more steps through here. He's talking about explain, which, the looking backward, the finding a model as the causal explanation, and explanatory modeling, again, explaining as the use of statistical models for testing your explanation. So has anybody ever done like a hypothesis testing, where you have your H0, and then you set up your alpha to say we want to have 95% confidence, and then you run your test and you either accept or reject your hypothesis. So there's like, if you ever see H0 and H1 or multiple hypotheses, that's all statistical, like theoretical testing. He's talking about predictive modeling here as the process of applying a statistical model or data mining algorithm to the data for purpose of predicting new or future. And so if somebody can explain this to me, like to me, he talks about, I focus on non-stochastic prediction. I can't find that anywhere on Google, like as to what that means. I know stochastic means that it's like data that has randomness to it. So I assume non-stochastic means it's non-random data, but if anybody watching this on YouTube can comment on what he's getting at there, I haven't quite figured it out. So just going through a few more slides here, the lack of a clear distinction within statistics has created this lack of understanding in many disciplines. And he's just talking about the difference here, let me just kind of point at this, between building a sound explanatory model versus creating a predictive model, and confusing explanatory power with predictive power. And again, that's like saying your regression line will predict the future, and it won't necessarily. Or moving averages is another, like time series. If you've ever worked with time series, they're trying to predict something. You're trying to watch a stock price and see where it's going. Well, if it was that easy, we could all just retire, right? So you don't just run a moving average and make stock purchases and get rich. So it's obviously not perfect at predicting the future. And if you look at the people, I don't know much about this, but you hear this term quants, these people that take machine learning to a real extreme degree, they're working on Wall Street, running these incredible predictive models. And I guess if you're right, 55% of the time you make a lot of money. Is it kind of like gambling? I don't know, but I don't know if anybody has that guy, the guy Ben Taylor, who does a lot of stuff up in Salt Lake City. He's from that background, and that guy's like major rocket scientist, way beyond my pay grade. Okay, so he talks here about, if you look at the end, he talks about regression models are the most common example. And again, if you're not familiar with what linear regression is, it really just takes, it's like least squares analysis. It just takes a set of data points and tries to fit a line to them and just makes the line as close to every point as possible. Tries to minimize that distance from the line. He talks about explanatory modeling is used for theory building and testing. Predictive modeling is nearly absent in many scientific fields as a tool for developing theory. And I think he's going to make some people mad here. He says one reason is statistical training of non-statistician researchers. I mean, I've studied a lot of statistics, and he's right. I mean, you don't see this distinction made. Statistics textbooks don't get into data mining. They don't get into any of this predictive analytics type of stuff. And I think he's got sort of a cultural thing he's talking about here, that prediction is considered unscientific. It's not, I mean, obviously it's academic now. Machine learning and data mining are being taught at universities. So to me, are we trying to understand what happened? Like, this is the explain side. Are we trying to understand what happened? Did we study a bunch of students in an online course, and we tried to see how effective was the course in teaching them? We're going to look at what happened and come up with an explanation of what happened in the past. Do we need a single model? Do we care about the model? Like, are we trying to publish some formula that explains why these students did well? Are we doing hypothesis testing? Then we're in the explain world. And if you're in the predict world, you don't, I mean, if you've got this, multi-petabyte data set, and if you ever look at what's called feature extraction, you could have like 50 to 50,000 variables that you're analyzing. I mean, it's amazing. Some of these machine learning algorithms will go in and try to find features, and you're not just looking at 50. If anybody's ever done like matrices or linear algebra, like just trying to deal with a few variables is complicated enough, but imagine trying to do 50 variables. Like, a human's not gonna understand that model anyways. So this is the point about prediction, is that you kind of get over the need to think that you're creating a model that you can understand. You just run the algorithm, and if it predicts accurately, that's what's important. This talks about multiple models. Let me just talk real quick about holdout data sets. If anyone's ever done any of this, you probably dealt with this in that one project that you presented, where if you have a data set, you actually, like, let's say you don't have enough data, you can actually do what's called cross-validation or holdout data sets. You might train there's like a training phase when you're running a machine learning algorithm. There's a part where you're running it on the data so it learns and tries, you tell it how to classify certain things, like with the classifier. You might have people talking about working on their Apple computer, or people working on their Windows machine or Linux. You would take some existing data and you'd tell the classifier which one is Apple, which one is Linux, which one is Windows. And then once that classifier has learned, then you put it loose on a different set of data called the test data. So that's what a holdout data set is, right? You have part of your data you're using to train your model, and then part of your data you're actually testing it. And if you don't have enough data, you can actually slice and dice the data differently. Like, you might take your first 70% and train, and then test on your last 30%, and then flip it around and train on your first 70%, test on your last 70%, train on your first 30. So these are all things where you're doing prediction. You're not really caring what model you come up with. Let's see here. So, and he talks about in section 1.4 of the paper, why do you have predictive modeling? Part of it is these new data sets that are huge. You may not even know what to measure. I mean, if you're going to hypothesize something and create a model, like, what if there's a pattern in the data that you don't know about? If you think that you can actually understand all the patterns and limit yourself to an explain approach, then you're missing out on what he calls newly measurable. It's actually kind of interesting because he talks about using predictive approaches to validate explanatory approaches. You know, if you have something that says my linear regression, my statistical model can accurately predict, well, you can test that. And this is what Ro's talking about on Kaggle as well. You know, like if you have a Titanic data set and you're taking part of it and training your algorithm to predict who dies, it's who dies, right, and who survives is the Titanic data set. Yeah, and so if you can come up with a model for that, and then you can use some predictive algorithms to prove that your model works, then that's even better. I mean, there is some crossover here. But I like his line here from the paper: a model either predicts accurately or it doesn't, and that can be observed. You know, I should present this next month. There's a whole thing. If you're familiar with confidence intervals, you know, like, you know, they say we know with 95% confidence that X, Y, and Z is true. Well, that means that 1 in 20 times you're wrong. So there's kind of a joke that 1 in 20 published papers is wrong, because if every published paper has a 95% confidence interval, then 1 in 20 will sneak in there. And there's even some work that talks about what's called p-hacking, and I should dig it up. I forget where I found this a couple months ago, but there's some work that says a lot of published studies are wrong. And then there's actually something that people don't realize. Like, if you hypothesize something, if you're a scientific researcher, right, or you're a sociologist, or you're well, not to say they're not scientific, but maybe not as scientific as a physicist, right? But if you're looking to publish something and you have a theory that you want to prove, what if you disprove your theory? What if you do all this work and you find out you were wrong? You don't publish that, right? There's a whole bunch of what's called unpublished papers that there's like a bias towards, you know, it's called confirmation bias. Like we all see, if we argue politics, right, or if we care about politics, we tend to watch the sources that confirm what we believe. We don't tend to go look at the other side. It's just the way humans are. And so to me, it's just kind of interesting to see, you know, how these things translate into this distinction between explain and predict. Okay, so he's making, I forgot to put my initial opening quote there, sorry. He's saying this is a straightforward way to compare competing theories. So let's say you have a data set and you have two different models that you're trying to test against each other. This, coming along with a predictive algorithm, would actually let you test. And I'm assuming that's what Kaggle is doing, you know, is that they know you're coming up with your model, or you're coming up with your analysis, and they know what the right answer is, so they can actually look at you and tell you if you're right or not. He does actually refer to a couple other papers. In his paper, he refers to, he sources a lot of other work, but, oops. I just like these lines here. You know, the predictive modeling has an important role, you know, in quantifying the level of predictability, and knowledge of unpredictability is a fundamental component of scientific knowledge. You know, like, what don't we know? What are we getting wrong? I think with that example I gave, maybe I'll dig it up for next month, but there's work done on unpublished papers and stuff that never, you know, stuff that hits the cutting room floor. And, you know, if you know your analysis is unpredictable, you can kind of be ready for what to do when you're wrong, because you don't get the grant, right? So, and can I just ask, does anybody in here work like in an academic environment? Do we have, like, I have not been exposed to academic environments much aside from being a student, except I worked at Huntsman Cancer Institute for a year, like doing Java programming and Apache Spark. And I'm not a genetics guy, right? Like, I learned, like, you know, this much about genetics, and it was an interesting experience being around all these PhD people and people. Like, on the negative side, if you're administering a federal grant, it's not like working at a startup, right? Like Kyle here in the front row, Kyle, right? Sorry. You know, he works at a startup. Maybe some of you guys work at startups where, like, there's a sense of urgency. I enjoy that sense of urgency. Like, people, they're putting on different hats. They're not saying that's not my job description. You know, they just get things done. And when I worked at Huntsman, they do great work there. Don't get me wrong, but it's not the same thing as working at a startup. You know, it's these PhDs. Or anybody in the room with a PhD? Okay, so I don't mean to knock PhDs. I kind of do this sometimes. You'll get my biases out. Like, I'll ask first, am I about to offend anybody? And, you know, PhDs are great, but man, they're so specialized and they're quiet people. Like, I talk a lot. You know, I'm pretty social, and, you know, I think you know, it was just an interesting environment to work at Huntsman. But these people are, they're doing really great work, and they're real smart. But I think that papers like this, like the woman that ran the research project I was on is a statistician, and I actually pitched them at one point when my work was wrapping up and I was trying to extend my work. I pitched them on instead of just doing a statistical analysis, let's try to use some machine learning. They had this genetic data they're working with. It's a pretty big data set. It takes a lot of computation. And they think they're applying, so just to kind of conclude this, and we'll move on to the next section, they're applying what they think works, but they don't know what they don't know. That's like the famous line, is that's the dangerous thing. And this goes, Donald Rumsfeld was famously quoted saying this, but it goes before him, is that we know what we know, we know what we don't know. It's the part, there's a third component of we don't know what we don't know, right? Like that's the part that'll get you. And that's where I think this paper is focusing in. That's where I think the power of predictive modeling, and these unsupervised methods in machine learning are really valuable, because you'll find patterns in data sets that you didn't know were there, and you would never have thought of it without this analysis. So there's a couple more slides here if anybody wants to go through and look at it more carefully. I kind of summarized the rest of the paper, talked a little more about the more data you have, the less variance you have, the less bias. And so, I mean, this is one thing I did want to cover. He makes, and again, if what I've said interests you at all, I would just suggest you sit down and read the whole paper. He talks about missing values. If anybody's ever done, like even if you do the basic Coursera, like data science courses, they have a course on cleaning, what do they call it, munging, right? How to clean data. And if maybe you've heard this, maybe not, that 80% of a data scientist's work is not like machine learning or data science, it's just cleaning data sets. And all data is dirty. You'll have, like if you look at some of the temperature data that the state of Utah puts up, there's missing values, right? Like sometimes the temperature sensor just didn't work. Well, you have to make a decision. And so I know in everything I've learned up to a certain point, they teach you to throw away your missing data. They teach you to figure out, how to fill it in with something. Missing data is bad. You have to have some way to make that missing thing a known quantity, or you call it an outlier. But this guy's making a really good point. He says sometimes the missing data is data. The fact that it's missing is significant. And so you could actually come up with multiple models. He has a section in this paper where he says that even if you're in the explain mode and coming up with a model, you might have multiple models, and one model has all the variables. Okay, like without trying to put you guys to sleep, like let's say one half of your data is missing temperature and the other half of your data is missing someone's height. Well, you have two models. One model doesn't need temperature, one model doesn't need height, and then you apply the appropriate model to where the data is missing. I just thought it was an interesting point that I've never seen brought up before, that missing data is itself data and can be used with machine learning methods, but it doesn't fit into standard statistical analysis. Like here, he talks about it right here. If you have only a small proportion of cases with missing data, you simply throw those cases out, right? We've all seen outliers where we just throw data away, and you do an analysis and say, is this within 3 standard deviations? If not, it's just a bad measurement. We'll throw it out. But if you want to make predictions for cases with missing inputs, you don't have the option of throwing those cases out all the time. So I have here he talks about exploratory data analysis, like cleaning. He talks about your choice of variables, validation. It gets into some heavier statistics stuff, and then he gets into that Netflix prize part and talks about another competition. So I don't know if anybody had any comments they wanted to make on that. It's a little theoretical, but I think it's worth understanding. If you don't take anything away, just take away the idea that explaining and predicting are two different things. He actually talks about something called descriptive modeling as a third option that he doesn't really deal with. It's basically visualization. It's like you have a data set, you just want to do some description. You want to make a graph. You're not trying to explain why or predict. So it's valuable to know that there is that third thing out there, but it's really and this paper came to my attention because it was presented at U of U. They have a data group there. It's their graduate students in their data management program, which is a really good program. If you're looking to, U of U is actually pretty good on the data science stuff. Utah Valley University, not so much. They have a data mining course, but that's about it. But U of U is really good, and U of U is getting there. They have their graduate computer science program now. I don't know if you've seen that. They actually have started a master's degree. It's not an MS, it's just an M. but it's pretty good. And one of the teachers there will kick your butt academically, I guarantee it. He's kind of a weird guy, but he's very challenging classes. Does anybody go to UVU or know people? Okay, good. I get myself in trouble here. So I want to move on to the second part of this. I don't know if I'm going to go all the way to 3:30. I kind of like have neck issues, and I'm trying to hang in there. And if anybody needs to take a quick break, just don't mind. Just go ahead and get up. But we want to get into basically Python and clustering. The reason I brought this up is because last week we had last month, Sydney presented, it's kind of a clustering approach, but just using binning. Let me figure out what I'm trying to show you here. Give me just a second. Oh, where's my, is it here? Yeah, here we go. And there's a little more advanced way to do clustering. And this is like I said, it's an unsupervised approach to machine learning. There's supervised and unsupervised. So supervised, these are just sort of like blanket definitions. There's more to it than this, but supervised basically means that you know what your data structure is, you know what features you want, you know what categories things are going to fit into. So like let's say you're trying to look at pictures of cars and predict if they're, or maybe not even predict, but just identify them, classify them as Toyotas versus BMWs versus Buicks. Well, you would, like I talked about before, you could do some training, or you could have some other way of analyzing what kind of car it is. You know in advance the categories that you're trying to come to. So that's something different. That's called classification. You hear about deep learning and neural nets are something I don't understand very well. So maybe John will give us a 5-minute pitch at the end. I think you know more about it than I do, but and John's going to present one of these days, maybe in January or December or something. But what we're looking at today is clustering. It's the idea that you actually don't know what your data structure is, and you want to find a way to classify the data that you may not have thought of. And so it's based on these things. I told you earlier about this guy named Jeff Phillips, who's a professor up at U of U, who he turned me on to the idea that machine learning isn't really statistics. It's more of a computational and what's the other word I'm looking for? Iterational approach, where you keep on, you're iterating and getting closer and closer to the answer. If you've ever studied calculus, you can have a limit where the actual point that you look at the limit, it's approaching a point where the function's not defined at that point, but the closer you get to it, the closer you get to knowing what the limit is. And this is kind of the same thing. It's where like I took this class up there called Foundations of Data Analysis. It used to be called Math for Data, and they've renamed it. You can actually, you can go online. If you look at the slides and you get to these links, you can see, like I'll click on this one here. Oops. And you can see he's teaching it this semester. So he doesn't have the homework 5 is not linked up here yet, but all these homeworks are available. And it goes through a lot of good stuff. It starts with a basic review of probability, Bayes rule, does a linear algebra review, regression. I might talk about PCA and gradient descent next month. I haven't decided. I want to do something more advanced on machine learning, but still, like, I'm not a rocket scientist, so it's not going to get that advanced, right? But basically, he's got this section here on classification. And so some of what I'm presenting to you is actually out of his paper. He's working on a book. But if you want to learn, this is, I think, a really great resource. He has these, if you look back at his homepage here for this class, he has all these different things posted. Like this is one, this is number 2, this is number 3, linear algebra review. But when you get into classification, just so you know where this material is coming from, like the chart or the graph I'm about to show you is coming from this. There's a lot of good math in there. Who's a math geek? Any math geeks in the room? Okay, we got 1 or 2 of it. Okay, so if you're a math geek, then you're going to like this stuff. If you're not a math geek, then you don't care about this stuff, right? You just want to write Python code and apply different algorithms and get some good results. But having a little bit basic understanding of what's happening behind the scenes is useful, I think. So let's jump in here. So the theory behind clustering is what's called Voronoi diagrams. And so if you're given data points, you're trying to find the edges and the points that separate the data the most cleanly. You're basically minimizing the distance of all the points from their center points. So I mean, that's pretty interesting, but you'll never need to actually implement that in an algorithm unless you want to start writing new machine learning algorithms. Because as we'll jump into here within about 5 or 10 minutes, there's scikit-learn, which has all the algorithms that more than I can even understand. Like at some point I'll show you a list and I don't even know what they all do. So I should at some point, but okay. So just a little bit of math stuff here. You know, part of what they're doing here is when you do an algorithm, there could be the greatest algorithm in the world, but if it's not efficient, like you could run it and it might take 10 years to finish. Like even with the kind of computational power we have today, there's algorithms out there that are great algorithms, but they'll never finish. If anybody knows what big O notation is, they teach it in algorithms courses where you analyze an algorithm to see like what's the runtime. So if you have a data set with like, let's say K, right? Let's say K is 10. You can run any algorithm on 10 data points because it doesn't matter if it's K to the 4th power, then what is that, 10,000, right? So it just takes 10,000 cycles of the computer to run if something is, you know, n to the 4th or K to the 4th, you know, it's exponential to the power of 4 to run this algorithm. You don't care if it's small data, but if you have bigger data, it literally will never finish. You know, you've ever studied the thing about like to teach people the power of squaring things? You know, you go to the king and he says, "Oh, you've done something great for me. I'll take it. I'll give you anything you want." You say, "Well, today I want 1 grain of rice, and tomorrow I want 2 grains of rice, and then the third day I want 4 grains of rice." And within like a month, you've taken all the rice in the entire kingdom. And so that's what's behind this big O notation. Who does know big O notation or has taken algorithms? Okay, so we got some familiar. So this is something good to at least be aware of if you're not familiar with it, because if you're going to do any kind of programming, you have to, if you're just using libraries, then you can assume the library developers have picked the best algorithms. But if you ever take like a data structures class, that's part of what they have you do is they show you how different sort algorithms work. You know, you have to figure out for the kind of data you're trying to sort, what's the best approach. So here he's just getting into some math and he's talking about the upper limit of these Voronoi diagrams, or Delaunay triangulation, I guess is the same result, 2 different mathematical approaches. But they talk about the complexity, right? And so it's O to the K of D over 2. So when they say stuff like this in R, and I didn't get the best mathematical notation in here, but R to the D means like if you're in 2 dimensions, that's R squared, right? You're in a 2-dimensional space of real numbers. If you're in 3 dimensions, it'd be R to the R3. But you know, there's data sets that have, like I said before, 50 dimensions, and you know, there's data sets that have 50,000 dimensions. And so the more dimensions of data you have, like every feature you're looking at could be a new dimension. You know, if you're looking at movie recommendations, I mean, I don't know, just off the top of my head, you know, there'd be like, did people watch the movie all the way through? You know, did they watch it a couple times? Did they share it? You know, you start thinking about like what variables you can come up with, and pretty soon you're getting way past 3 dimensions into. So it's important to know. I mean, every time you add a new variable and run it through some algorithm, this algorithm is sensitive to the number of features that you have, of variables. Otherwise, O to the K isn't bad, but O to the K of D over 2 can get out of hand pretty quick. Now he makes an interesting point here. Like we hear people say K means algorithm. Don't ever say K means algorithm. You'll sound smart, but you won't be technically correct. It's actually a formula. The algorithm behind it is called Lloyd's algorithm. And so there's, like when they say K means, and we'll see this when I start showing some code pretty soon here, it's actually a family of algorithms. It's not a single algorithm. It's a way of classifying data or clustering data. So in his little document there, Jeff Phillips says don't say K means algorithm. So I thought I'd pass that along. And again, for the math geeks, you know, this stuff all has like real math behind it. The clustering is basically a cost function, and maybe if you're from like a management background, that also sounds familiar. You know, like if you look at, like I've been lucky enough in the last year to also study operations management, and like lean management and quality management, all this stuff. And you know, there's these cost functions. You have like 3 factories, and you're trying to figure out which factory should you produce something at to have the least delivery cost. And that's a lot of this type of math gets applied there too. So you're basically trying to divide up your data into clusters and decide, you know, what set of center points on your clusters is going to give you the lowest cost. It's a cost minimization. And this is a good point to bring up. When the data is not easily clusterable, you won't find good clusters. So if you're trying to run clustering and you're not coming up with an answer, you know, that's probably why. Now, some of the examples we'll get to will visualize the data for us, and you'll see that like for different types of data, different clustering algorithms work better. This is just kind of like going to make your eyes roll over. So let's not like read through this, but basically he's talking about how you're finding, if you've ever done calculus and try to find like local minima and maxima, versus global, what's the term? Like actual minimums and max. You can run calculus on a formula and find a minimum, but then you have to do more tests to see if you've actually found the global minimum or whether you just found a local minimum. Because like let's say a line, like a sine wave, right? Every time that sine wave hits the bottom, that's a local minimum. But then if you look at a bigger picture, you're going to have maybe something. So when you're trying to do a minimizing, like a cost function, the point he's making here is that you run your clustering algorithm several times, and then that's how you get away. That's how you get around, finding the wrong answer, finding the wrong minimum. Now this is something we're going to look at live in a minute here, but that's what I was getting at. Is there, if anyone's ever seen in Python, I forget the name of the library. We'll look at it in a minute. It's for making data sets. There's like a moons, right? These sort of moon-looking things. That's moon data sets. There's names for all these different algorithms, and you can actually see these different, mini batch k-means, affinity propagation, mean shift. I'm looking at the titles up on the top here. Spectral clustering. This stuff all sounds really cool, right? Like agglomerative clustering. Like what? I don't even. I know what it does, but I don't know what it means, honestly. And you can see for different data sets, it's actually like, just look at here on this circular data set. This algorithm just neatly split everything into two clusters. Everything on the left is, what color is that? Like brownish, is that ochre? I forget. And then on the right is blue. All of these different algorithms did different things with the data. So there's a point that's made here that this is, again, like it's a method of trial and error. You've got to see what algorithm does the best in your data. There may not be, kind of reminds me of the explain versus predict thing, because there may not just be one answer. Now, we're going to get into scikit-learn, and I don't know, again, people have different levels of Python knowledge in here, but you use all these different libraries. Like here, NumPy is a library for managing arrays and doing, math. sklearn is the scikit-learn library, for doing machine learning. Let me bring up. I don't know if I'm going to do it in a notebook or if I'm going to do it in Spider. And just a quick aside, if you've never seen Spider before, I was talking with you about Anaconda when we first started. So if you ever want to do data science with Python, the first thing you do is you download and install Anaconda. If you're in Linux, I could help you with that. If you're in Windows, I'm not totally familiar with how to do that in Windows. The Mac should be similar to Linux. But Anaconda comes with a Python IDE called Spider. It's not very good with Jupyter Notebooks in my experience. There is an extension for notebooks, but I like PyCharm. But I just wanted to make sure I'm not sure that we're going to look at too much stuff in Spider here. But this is, when you look at Jupyter Notebooks, and I'm just doing a quick aside. Jupyter Notebooks stink for one thing. They stink for writing complicated programs. There is a debugger in Jupyter Notebooks. Has anybody ever used PDB? Yeah, PDB is like a text-based debugger for Python. Sorry, I like these graphical type things. Like I ran this program and I can actually see the values of my variables up here. I have this array of objects of NumPy. I can actually double-click this and see what's in it. I like using an integrated development, an IDE, right? Integrated development environment. Notebook, and I've taken classes where I watch these students, like they're doing like really complicated stuff in notebooks and they have no idea how to debug, and no wonder they're like beating their head against the wall and spending hours on it. So before we get into code here, a lot of times I actually take code over to Spider or PyCharm, work on it there, and then copy it back to the notebook. So I just don't want to leave anybody with the impression that notebooks they're great for presentation. I don't think they're all that great for development. Let's take a look here. Basic machine learning, and this is available in the repo that I put up. This is actually just taken from the scikit-learn. Do I have it up here? Let me actually bring this up. Thanks for coming. See. Yeah, go ahead, please.
So if you're learning and you're just having trouble, just maybe even like simple commands, it might be easier to throw that in Spider and figure out what you're mistyping. essentially, and then going back to if you're struggling with just learning how to do the basic coding.
I think at that level, I think Jupyter Notebooks actually kind of shine because if you're just trying to figure out syntax and commands, I mean, Spider, let me show you in Spider real quick. It has, if I can get my fingers to work.
So yeah, that's it.
Okay, thanks for coming.
If you're just, if it's the syntax that you're struggling with and just getting it right.
I mean, Spider has what's called an IPython. I've got a bunch of errors in here that I was going to show you, but I mean, you can come here like one of the most common things that I stumble across is in Python 2.7, you would just say print hello, right? Well, that doesn't work in Python 3. If you're not familiar, there's Python 2, which a lot of people still have things implemented in because it's not, Python 3 is not fully backward compatible with Python 2. But I think pretty much everything you're going to start new is going to be in Python 3 now. So you notice that didn't work, right? And so, okay, I got my syntax wrong. I need a parenthesis there, and then close the parenthesis, and it works. So, I mean, you can do that here, or you could go into Jupyter Notebook. Where'd I go here? You can go into a notebook, and let's just make a new notebook here. And it's a really good question. I'm not going to spend too much time on it here, but basically, to me, this is just as easy to come in here, print. I mean, and then when you run it, you get the same error. So unless I'm missing your point.
No, you got it.
Yeah, I think notebooks are actually really good for people just learning. I think it's when you start writing more complex programs that you need to debug, and you want to actually be able to, does everybody know what breakpoints are? Like when you're debugging a program, you can set a breakpoint and you stop your program so you can right before it blows up, you stop it and you start looking at your variable values and figure out what you did wrong. And you can do that here, but it's just, and I've talked to the guy that's like the main developer on Jupyter, and he actually met the guy. I was in San Luis Obispo a few months back, and I was in a Starbucks one day, and this guy, if you know where Los Osos is, it's out by the beach there, and this guy's on the phone, and he's actually holding like a meeting with the people that developed Jupyter. And he turns out to be a guy named Brian Granger. He's a physicist at Caltech there. And, I mean, he's a busy guy. It's not like I'm going to bug him a lot. But I said, I got one question. Is there a real debugger in Jupyter? He goes, no. People complain about that a lot. But so, okay, so I think you ask a good question. And I think if you want to learn PDB and learn text debugging, then I'm impressed because I've never had to do it, and I just am not interested. And I'm sure, I mean, I've had to do like distributed debugging. Like with Spark, you have processes running on a bunch of different machines, and I've had to figure out how to attach to a process across a network. But that's different, right? Like that's still graphical and fun. And so, okay. So did you have any follow-up? Okay, cool. Yeah. But I think that's helpful for people because I mean, especially if you're just kind of learning Python and then you're looking at some of this more advanced stuff, and I'm kind of just trying to blast through it here. Let's get back here, and then let's go look at that notebook again. Okay, so I'm going to close this. And just to mention, I mean, Jupyter Notebooks run on a Jupyter Notebook server, just in case you're not familiar with this. So when you close a notebook, you haven't necessarily, like if I do a ps aux grep Jupyter, Jupy, I've got, like every time I close a notebook, it doesn't kill the process unless you explicitly tell it to shut down, like just closing the window. And then I'm just saying this just while we're kind of talking about a couple basic things. Like if you try to restart a new notebook and it says that port's in use or it can't do it, it's probably because you haven't killed your old notebook servers. But you can see these, you can see like here's the basic machine learning IPython notebook, process running. But I've got all these other processes hanging out that aren't really doing anything, that are just taking up, CPU cycles. Okay, but let's take a look here. I mean, the results of this, let's see, did I run this? Yeah, I mean, the results of this are that graph we were looking at. And so what I wanted to do just in the time remaining, and I may not go all the way to 3:30, or we'll see if there's any discussion, but I'll probably just run through this for about 10 minutes. And let me go back and look at my slides and see if there's anything that I'm missing here. I mean, we'll look at this in the code. There's these different clustering algorithms that you saw represented in that graph. And again, I provide the slides mostly because I don't expect anybody to memorize this, but here's a link down here, and you can actually click on that link if you look at the slides. And it's in our, I don't have it up right now, but it's in our Slack group. Let me show you this real quick before we hit the home stretch here. Chrome, where'd it go? Oh, that's my Hangout. Oh, sorry, guys. Okay, if you look at our Slack group, it's actually in the general. I've been posting a lot of this stuff. So right now, here's the repo. Here's one of the slides. And then, yeah, so if people don't know how to get to this, it's provolab.slack.com. Or is it, does that work? I think, yeah. And then you have to get an invite to get in. But so if anybody's watching this later and wants access to the slides, you can see the links in there. Or anybody here wants that, you can go there. And then here's the repo I have on GitHub that has the notebooks. And it has some other notebooks here too that were provided as part of that Coursera class. All right, so let's hit the home stretch here. It's getting kind of late in the day. At least BYU is not playing in town, right? Like when you leave here, you're not going to be fighting traffic. And who likes BYU football? Is anybody? Oh, good. Okay, so that's why everybody's happy here, right? Is because if anybody's followed it, my ex-wife works at BYU and they're not happy with their football team right now. If they've lost almost every game, I think. So hopefully today's a win. Okay, so you have this k-means algorithm. I clicked on the link and this is the documentation for it. But let's actually take a look at the notebook and run the actual code here. Basic. And this is the notebook called Basic Machine Learning. So you import. One of the things that I think was real interesting about this is that you can have warnings come up. I'll show you this in Spider. In the code I suppressed. They have something that suppresses warnings, and I commented that out. And when you run it, you get all these warnings about, what is it? Your hierarchical.py doesn't like your number of connected components of your connectivity matrix. It's 78 instead of. Who cares? I mean, does it run or not, right? Like if it's a warning, probably to our detriment, we tend to ignore warnings. And so there's a way to turn that off, and that's why you're not seeing it over here on the notebook. So we import this library called warnings. We import NumPy, matplotlib, and then here's where the rubber hits the road here. sklearn. You're importing these libraries called clusters, data sets, and mixture. And this is an interesting part to me. This is where they're generating, like if you don't have a real data set to work with, you have to make a fake data set. And if we remember down at the bottom, there's each one of these horizontal rows is a different data set. And so just remember here, like the first one is 2 concentric circles, the second one is the moons. They have some pretty cool names for all this stuff. And so you look how they start out, and they're actually making noisy circles. They're introducing noise, which is a different subject we're not going to get into today. But they make this variable called noisy circles. They're using this data sets library. So Python has, like if you ever think of writing something like this for yourself, like do it if you want to learn, but otherwise it already exists. You call data sets, you call a function on data sets called make circles. You notice our samples are 1500. You're just setting the noise factor, and boom, you get a data set called noisy circles, and then ultimately it's going to get. Let me do this. Ultimately, going to get graphed to look like that. The next one is going to be moons. So it's there's a variable here called noisy moons, and they're calling data sets make moons. Pretty simple. Same thing. 1500 samples, a noise factor of 0.05. I guess the third one is blobs, and the fourth one is no structure. Is that? I think I can actually. Where was my example? Was it here? Yeah. And again, this is all being drawn from this tutorial, I guess, or comparing different clustering algorithms on toy data sets. So there's, what were they called again? I think I would say this is probably the no structure one. And then. Okay, so we keep on, sorry, I keep flipping here. One more flip. Yeah. Back to my, so you go through here and you make more data sets. And this is another example where you're calling something in data sets that's going to, this make blob is going to return an X and a Y. And so you're actually giving it, this is like I say, if you're from like a Java or C++ background, you don't normally see this, but this is like a Python, and I'm getting familiar with Elixir. Elixir does this. I'm sure a bunch of languages do, where you're expecting 2 return values, so you just assign them to 2 variables. They're making another data set here. So they spend some time just setting up these data sets to analyze. And then they're setting up some parameters on their clustering, but this is where they actually get, they're basically building the structure here. You notice it's a list. It starts out with a bracket, and then it's a list of tuples. Inside the list, the next thing is a parenthesis. So these are actually tuples here. And then if you look one level deeper, and I'm just kind of doing this if you're not that familiar with Python, these are not maps, dictionaries. When you see these curly brackets, so you'll see in a dictionary, you'll see a key and a value, and then another key and a value. So they're basically setting up a list of tuples with the name of the, or with the actual data set, and then some parameters for the data set. And then you'll see at some point here, they're going to do this for statement. And they basically just say it has the same structure, right? It's a data set and a tuple. So I've actually never seen a for loop done this way. I think it's pretty cool. I'm going to keep this in mind for the future. You're enumerating through something made up of a list of tuples with a dictionary in it, and you're actually, every time you iterate through, that's what you get back. And then they're assigning their X and Y. They're doing a fit. And the actual graphing is happening a little further down here. Because the for loop is going through all the different types of data sets, and then this is going to actually go through all their different, you see they have their mini batch k-means. If you see where the mouse is here, agglomerate clustering. So for every data set, they're running all these different methods, and that's how they're making that pretty cool chart down there. And I think the point, if you want to figure like what to take away from all this, it's showing that even though they're all k-means and they're all probably roughly under Lloyd's algorithm, they all have different effects. So I don't know if anybody has practical experience with doing this like in a work environment. It's an iterative approach. I mean, you have to try different things and see what works the best. I don't know what would get the best vote here on this data. I think it's interesting how the square data down here is probably the most interesting to look at to me. Let me make this a little bigger. And you can see, look, this one clustering algorithm right here didn't do a very good job, right? So it's probably, like this guy on the left. But again, it's just interesting to see. And you can specify how many clusters you're looking for. So some of that's driven by the parameters they're sending. But that's about all I have to present on this, and we're coming up towards the end of our time. I don't know if anybody has questions at this point. I mean, if anybody wants to look closer at that code, we could probably do that offline here. But if not, is there any questions at this point, or anybody want to make some comments? Sometimes sklearn leaves me speechless too. So, but yeah, I'm probably going to wrap up the broadcast here at this point, a few minutes early, and I'm starting to fade out. You guys probably are too, and I appreciate your attention today. Thanks. Thanks, appreciate that. Thank you. Okay, let's stop and stop the broadcast.